Okay, so today we're going to be talking about power off stalls. So the objective of today's lesson is for the student to be able to understand all elements associated with the power off stall during different configurations, pitch attitudes, bank angles, along with knowledge of common errors on how to correct them. So what is a stall? A stall occurs when the smooth airflow that adheres the wings is disrupted and causes a loss of lift and increased drag. This happens primarily when the wing's angle of attack, which is the angle between the chord line and the relative wind, exceed the critical angle of attack. And we're going to talk soon about what the critical angle of attack means. Power off stalls are practiced to simulate stalls in the approach and landing phase of flight. It can be done in the landing configuration. So on the whiteboard behind me, we're going to talk a little bit about what gives the plane lift, because during a power off stall, you're simulating losing that lift and stalling the plane. So this is what our wing looks like, right? And then this is something called the chord line. Just goes from the edge of the wing to the front of the wing. And then so say so we're going this way and our relative wind is coming this way. The particles of air on this side of the wing are going to want to get to the other end of the wing at the same time. So since they have a longer distance to go over top of the wing than they do below the wing, these particles are going to have to move faster in order to get to the end of the wing at the same time as these particles. And these particles moving faster is going to give the air above the wing a lower pressure than the air below the wing, which is going to have a higher pressure. Can I get a new marker? And because of Bernoulli's principle, we know the high pressure is going to want to go to the low pressure, which is going to give us that lift. Now, so that's how a plane flies in a normal situation. Now, when we pitch up, oh, that's really bad. Hold on. When we're pitched up, here's our chord line. And the relative wind remains the same. So now, here's the relative wind again. Now our angle between the chord line and the relative wind is going to be this angle right here. Let me see if I can get a better marker so that you guys can see this a little bit better here. All right, hopefully that helps with the glare a little bit. So yeah, so this is our angle between the relative wind and the chord line. This is going to be our angle of attack. So the critical angle of attack is when our plane is not able to create lift anymore. So when the wind goes over it, at this point, the wind can still go over and create that pressure differential. But at a certain point, the wind is going to go below it, and then going over it, it's not going to create that smooth airflow, and it's going to topple over the edge. And this is when we stop creating lift. And so our critical angle of attack is when the airplane stalls, and then it's going to go nose forward. And that is what we are going to be simulating with our power on stall. So yes, here's another picture of it here. Here's a normal angle of attack. This is getting a bit higher, and this would be close to the critical angle of attack. So why do we practice stalls? Stalls are practiced to improve the recognition and recovery of a stall, and ultimately to prevent the loss of control of the aircraft. While practicing stalls, the student should gain a better understanding of the stall characteristics of the aircraft being flown by developing these skills and recognition. So by practicing it, we can easily identify when the stall is happening, and we'll talk in a minute on what are the signals of identifying a stall. And then we can also practice what to do if we are in that stalled configuration and how to recover from it. All right, so yes, it is vital that the student understands how they happen, why they happen, how to avoid them, and how to recover from them. So, we'll do a little review. We've got the 4 phases of flight. I just mentioned lift. Lift is the force generated by the wings that opposes gravity and enables the aircraft to fly. And we've got weight. Weight is the force of gravity acting on the airplane. Thrust is the force generated by the engine that propels the aircraft forward. And drag, which is the aerodynamic force that opposes the aircraft motion during the air. So if this is our aircraft, this is lift. Oh, sorry. All right, so this is our aircraft. This is lift. This is thrust. This is drag. And this is weight. I'll make that bigger. You can see it on the video. All right, so the stall speed is the speed at which the airplane will exceed the critical angle of attack and no longer be able to create lift, and that is when the plane will stall. So there are a couple of factors that go into changing this stall speed. A couple can be the configuration. So extending the gear or flaps can impact the stall. Both will increase drag and flaps increase lift. This increase in lift will reduce the speed in which the aircraft will reach the critical angle of attack. So this will lower the stall speed, and this is good. So in the power off stall, we'll actually be putting in flaps to simulate when we're coming into land. Things that increase the stall speed are going to be bad because that means that you'll more easily reach that critical angle of attack and stall, which is not good. We don't want to stall. So we are trying to avoid that. Weight, as the weight of the airplane is increased more lift is required. So back to this, if we got more weight, we've got to have more lift to maintain straight and level flight. And this generally results in a higher angle of attack. So if we got more lift, we're going to pitch the nose up more to create more lift, and that creates a higher angle of attack. And thus the plane will stall at a higher indicated airspeed. So this increases our stall speed. All right, and then we have the center of gravity. In the case where the aircraft is loaded with the forward CG, it will feel heavier and will consequently be slightly slower than the same aircraft in the same configuration loaded with a more aft CG. This configuration requires a higher angle of attack, thus a higher stall speed. However, due to the longer arm between the center of gravity and the horizontal control surfaces, the aircraft is somewhat more controllable. So if you got a forward CG, you're going to have a higher angle of attack, and therefore your aircraft will stall at a higher speed, but it will be more controllable, so it will be easier to recover from that stall rather than having an aft center of gravity. So with an aft center of gravity, you actually are going to have a slower stall speed, but we will talk about how with an aft CG, it is much more difficult to control the plane, therefore making it more difficult to recover from the stall. All right, yes, and then we have load factor. Load factor is the ratio of the total load acting on the plane on the airplane to the gross weight of the plane. The airplane's stall speed increases in proportion of the square root of the load factor. Therefore, a plane that stalls at 45 knots could be stalled at 90 knots when subjected to G's. So this could be if you're in a steep bank or pitching up rapidly. This condition is known as an accelerated stall. So yes, that's a different stall that we're not going to be talking about today, but that will cause you to stall at a much higher speed. And then we've got snow, ice, and frost. Any frozen moisture on the wings can raise the stall speed significantly. This is due to the basic shape of the wing being changed and the additional surface roughness that disrupts the smooth airflow over the wing. So yeah, snow, ice, and frost is not good. It changes the surface of the wing, and they're made very specifically to create that lift. So before any flight, you should remove all frost or snow if possible. And we also have turbulence. The presence of turbulence can cause the aircraft to stall at a higher airspeed. A vertical gust of wind shear can cause a rapid change in the relative wind, which can result in a greatly increased angle of attack. This increase can exceed the critical angle of attack, thus resulting in an immediate stall. So this is if you've got a lot of turbulence or wind shear, you can actually find yourself in a stalled condition very quickly. So it's important to be able to react to that immediately and put your practice to use from stalls. All right. So the procedure for practicing the stall. So stall, we'll just go over the definition again. The loss of lift due to the separation of airflow over the wings brought by exceeding the critical angle of attack. Stalls may occur at any airspeed, attitude, and any power setting. So just because you've got full power doesn't necessarily mean that you can't stall. And just because you're at a straight and level flight also does not mean you can't stall. So stall types, we've got an imminent stall, which the aircraft is approaching the stall with early warning signs such as the stall warning horn, buffeting, or mushy controls, but has not exceeded the critical angle of attack. And then you have a full stall, which is when the aircraft has exceeded the critical angle of attack and will begin to get shaky and the nose will drop. So when you're on the check ride and the examiner asks you to do a stall, he'll probably clarify either if he wants you to go to a full stall or first indication. First indication is going to be this imminent stall here. And if he doesn't, it would be a good idea to ask him. If you forget to ask and you're in the middle of the stall, just recover at the first indication. So the first indication will be any sort of indication of the stall. So the stall warning horn will probably happen first, but it might not. You might feel the plane buffeting. So if you're kind of losing control, that would also be a first indication of the stall. And at that point, you would recover, which we will talk about how to recover in a minute in this lesson. All right, so how to do it. So first you want to select a proper altitude for the maneuver. With a power off stall, you are simulating a landing, so you might lose a little bit of altitude. So it's important to do this at a high enough altitude that you will be able to recover from this. So no lower than 1500 AGL. I would normally do it at least 2500 AGL, but that is up to you. And then perform clearing turns like you do any maneuver, 2 90-degree turns or a 180-degree turn. Then you want to scan for outside references, altimeter. You look at your altimeter, your airspeed indicator, your heading indicator, and your compass. And make sure that you're in straight and level flight and bug your heading because you're going to want to come out of this maneuver on the same heading. You should not be turning at all. All right, so, and then you want to do your pre-maneuver checklist. So just kind of a mental checklist. You want to make sure the mixture is full forward, make sure your fuel pump is on, and make sure all your engine indications are green. I'm going to start the maneuver. Looks like I'm glitching a little bit. There we go. Then you're going to start the maneuver. So since we are simulating coming into landing, you're going to start the maneuvers pretty similar to how you would land. So you're going to pull back the power to your approach power setting, which on the Archers is about 1500 RPM. And then you're going to start adding in flaps as soon as you reach VFE. So in the Archers, that's 102. Which you should be starting this maneuver around 100 knots anyway, so you should be able to go ahead and start putting in flaps right away. And then pretty quickly add each notch of flaps until you're at full flaps. And then once you're at full flaps, you want to establish a stabilized descent at the standard aircraft approach speed. So for Purdue's Archers, it's going to be 66 knots. So this is like you're on final, you're just going to start pitching the nose down as if you're coming in for a stabilized descent. And you want to make sure you're applying rudder as necessary to stay coordinated throughout the maneuver. And then you're going to initiate the stall. You're going to go power to idle and then maintain descending. And then you're going to pitch the nose up, increase back pressure on the yoke smoothly to induce stall. But you're not going to need to pitch the nose up too much for this because you're already very low power. So you're really just going to need to bring the nose to the horizon, maybe a couple degrees above horizon. And you might be asked to perform this while turning to simulate stalling like a base to final or a downwind to base. So if you are asked to do that, this is after you bring the nose up, you can start a smooth turn. And then once you have that first indication of a stall, you might have to be patient. Sometimes it takes a minute. So you don't want to get impatient and bring the nose back as far as you can. Just hold the nose on the horizon. You'll start bleeding off airspeed pretty quickly at that point until you get to the stall speed and you reach your critical angle of attack. As soon as you hear the stall horn or you feel a buffet or you start to lose control of the airplane or the nose drops, that is when you would announce the stall. So you can announce imminent stall, and then you would recover. So the recovery, the first thing you're gonna want to do is reduce the angle of attack. So pitch the nose down. You don't want to dive down because you're on landing, so the ground is pretty close beneath you. But you do want to break that stall. So you're going to pitch the nose down and then immediately after apply full power. Keep in mind when you're applying full power, you might need some right rudder correction due to that left turning tendency. So yes, you might need some right rudder for that because the engine is spinning to the right. So the plane is going to want to go to the left because of Newton's third law. Every action has an equal and opposite reaction. So since you're applying full power, you're increasing that force. So you're going to need to apply right rudder. And then make sure your ailerons are in neutral if you were banked previously. And you want to immediately retract that first notch of flaps as soon as possible because that third notch is really just creating drag. And so then you want to pitch for VY. So we'll pitch for 76. Once we get to 76, then we'll start taking out the rest of the flaps and return to the specified heading, airspeed, and altitude. So if you weren't in a banking turn, you should already be at that heading because you should have kept the turn coordinated and been looking outside at your reference and in at your instruments throughout this whole maneuver. That's pretty important. You're gonna be pretty focused on your airspeed indicator, but you also want to make sure that you're scanning all of your instruments, your attitude, your heading indicator. You want to look outside at your reference point. This is still VFR, so you should also be scanning for traffic every once in a while. And then at the end of the maneuver, you should be straight and level. And you should not have lost too much airspeed. It's normal to, altitude. It's normal to lose a little bit, but you shouldn't lose more than a couple hundred feet. All right. All right, and then on higher density altitude days, the stall speed will also increase. So that's important to note. Okay, yes. So remember I talked about heading on the private standards, you get plus or minus 10 degrees on your heading. And then bank, you get plus or minus 10 degrees as well. And then you must acknowledge the stall and recover from the stall. Commercial, it's the same thing, plus or minus 10 degrees. This is actually when I was taking my commercial check ride, my examiner noted that this is actually where most people fail on stalls in slow flight, is the heading, because you're so focused on your speed that you forget to stay coordinated and maintain your heading and adjust for wind. So you do want to make sure you're glancing at your heading indicator every once in a while throughout this maneuver. Bank plus or minus 5 degrees though for the commercial instead of 10. All right. All right, so some common errors in proper correction for torque effect. So we talked about that. When you're applying full power, you're gonna have that torque to the left. You wanna use your right rudder. Stalling after attempting to recover from the maneuver. So when you're recovering and you pitch up after breaking the stall, you wanna make sure you don't do that too quickly because you might have a secondary stall, which is going to be more difficult to recover from. So yeah, so to correct that, just relieve the back pressure to return to level flight. You shouldn't be doing anything too drastic. And you want to make sure you reduce the angle of attack far enough and for long enough that you allow the airspeed to increase again. All right. You don't want to over rely on your instruments too much. You should be looking outside. You should be able to feel the plane. Losing that airspeed, you can hear it from the engines. So you don't want to be stuck inside the entire maneuver, but you do want to be referencing your instruments. And make sure you stay coordinated the whole time. Keep glancing at that slipskin indicator. Make sure the ball's in the middle. Use your rudders if needed. Yeah, okay. I think that's about it.